Check it out now, y'all.
NanoHub U, online instruction.
Well, welcome to tutorial 1.3, and this is a problem where my purpose is a little bit to illustrate a concept that people who work with conductors who think of resistance are quite used to, and that is this important difference between what are called degenerate conductors and the non-degenerate ones. And often real things are somewhere in between, but each one of these kind of gives you a different way of thinking about it and is often a good approximation. And I wanted to give you a feeling for what's involved here. And for this, a good starting point is this expression for conductance that we obtained. You see, the conductance involved this integral over energy, and then there was the derivative of the Fermi function, and then there was this quantity. That's kind of the conductance of a particular energy channel. So the way you think about it is that current flows, electrons flow with different energies, and at each energy there is a certain associated conductance, and this represents some kind of an average over that. And so in much of the subsequent discussion, I often said, well, we don't really need to carry this one around. Let's just talk about the conductance of a particular energy. And then we know that at the end of the day, if you want an actual number, you'd have to integrate and you'd have to average over energies. Now, this idea that I said that this is sort of like an average, taking an average over energy, that's the point I want to clarify a little bit. Okay. Now, it's useful to have in your mind a picture of what this function looks like. That's this derivative of the Fermi function. You see, the Fermi function we defined in the lecture, and if you remember, the way it looks is, if this is energy, if you plot the Fermi function, there is this electrochemical potential mu 0, and above it, it goes to 0 and then goes to 1, changes from 0 to 1. And the way you see it from the function is that when E is a large negative number, that's when this exponential of a negative number is almost 0. And so you have 1 divided by 1 and the answer is 1. When E is a large positive number, this is a very big quantity and so 1 divided by a big quantity is 0. So that's why the function goes from 1 to 0. Okay. Now what's the derivative of this? Well, we can do it mathematically, but roughly, of course, you can see physically what it should look like. If you take the derivative, so this is F0. What I'm trying to draw is minus del F0 del E. And you can see that the derivative down here is 0 because it is basically fixed at 1. So when it's not changing. So there's no derivative here. Up here it's 0, again it's not changing, so it's all 0. It's around here that things are changing. So if you plot it, it would look something like this. Okay. So that's what this derivative of this function would normally look like. Now, what is the peak value of this function? Well, for this, we could evaluate the derivative properly. So if you write F0, see, it looks like 1 divided by e to the power x plus 1 if I define x as E minus mu 0 over kt. Then you can write F0, this Fermi function, as 1 divided by e to the power x plus 1. So when I take derivative of that, so I'm trying to get del F0 del E. So that's like taking the derivative of F0 with respect to x. And if I take the derivative of this, as you know, you'll get e to the power x plus 1 whole squared. and then I have to take the derivative of the e to the power x, which goes here, and there's a negative sign here, but I could take out the negative sign and put it here. So, I want the negative of this anyway. So that's that. And then I have to multiply it by dx dE, which is times 1 over kt. So that's what this function looks like if you actually wrote it out. And its maximum actually is that at that point x equals right here. And that's the point where x is 0. And when x is 0, it is e to the power 0 is 1. And this is 1 plus 1, 2 square. So that's like 1/4. So what you can see is that the peak value is like 1 divided by 4 kt. That's the nature of this function. Okay. Now, what is the width of this? As you might expect, the width kind of depends on kt, because you can look at that function, you could plot it out, you can see it actually depends on kt. And the important thing is that the area under this curve is actually 1. So it's like the height is 1 over kt, width is like kt, and the area is 1. Now, how do I show that the area is exactly 1? Well, the straightforward way would be take this function, integrate it. But actually, there's a quick way of doing this. So let me just show you that quickly. It works something like this. So I've got this function minus del f0 del e. And what I want to know is what is the area under the curve when I integrate over energy. So I multiply by dE. And I integrate from minus infinity to plus infinity. Okay, so this is easy because, you see, this is basically just df0 at two ends. So what you really have is f0 at minus infinity minus f0 at plus infinity. You see, because of that negative sign, I've reversed the limits of the integral. And the Fermi function, as you know, has the property that this is 0 and that is 1. And so the area under the curve is just 1. 1 minus 0 is just 1. Okay. Now, what I asked you to show in this problem then is that, well, if I had a conductor for which this quantity is almost constant, you see, over the entire energy range. So what I mean by that is, let me take this off. So supposing I am looking at this conductance, this is part of it which represents the conductance at a particular energy, this q squared d over 2t. So let's say we are looking at that quantity, and it looks like something that kind of looks like this. So what that means is, over this entire energy range, let's say the value doesn't change all that much, nearly constant, let's say. So then you see what I could do is, take that value, whatever it is, and just pull it outside the integral here. Because we say that, well, over the energy range where I'm doing this integral, it doesn't matter. It's almost constant. It's almost constant, so I can treat it as a constant and take it out of the integral. Okay, but in that case, integral this is just 1. And so you get the result that I asked you to show, namely that G is just q squared d over 2t evaluated at mu 0. So if I have to multiply this by, what I'm supposed to do is multiply this by this and then integrate over energy. But over this energy range, it is essentially constant. And so what I'll get at the end of the day will be roughly whatever this value is in the middle of that range, somewhere around there. So that's basically what I asked you to show. Now, this is an example of what one would normally call a degenerate conductor. That is one where, you see, over the entire energy range, essentially this is almost constant. This is what is usually true of metals. Now, on the other hand, you also have all kinds of other conductors, like say semiconductors, where when you look at the conductance as a function of energy, it doesn't quite look like this. It might look, say, something like this. In other words, the allowed band of energies could be much higher than the electrochemical potential here. So there's the electrochemical potential is somewhere here, and the actual allowed band is somewhere up here. Now, in that case, you see, you cannot quite say that in this band of energies, the conductance is constant. Well, it is, but then basically it is just zero around here, because there are no states here. So does that mean something like that doesn't conduct? Well, it's a semiconductor. It does conduct, but the conductance is because of this tail out here. In other words, this of course goes on, dies exponentially, but there is this tail out here, and that's the part that contributes to the conduction. And so the actual conductance you get would be due to these channels up here, but they would be severely cut down because you are looking at the tail of this function. And these are what you generally might call these non-degenerate conductors. And in fact, there's a common approximation people use out here. And that is that you see, I had mentioned before that the Fermi function, let me change the pen. Mentioned that the Fermi function looks like E minus mu 0 over kT plus 1. Now, in a non-degenerate conductor, because all the relevant energy channels are way above mu 0, it's like the region where it matters, this quantity is always relatively big. And so this exponential is relatively big. And it's not very important to include the 1. And so in that case, often people approximate this by saying exponential minus E minus mu 0 over kT. And this is what's often called the Boltzmann approximation. See? That instead of this Fermi function, you're using the Boltzmann function. And this is appropriate for non-degenerate conductors where all the conduction is at the tails. Now, the picture I've generally been using in describing things is more the degenerate case, which is where the conduction is something like this. And so basically you have got all these levels conducting. And if you can find the conductance at one energy, it is roughly representative of what you expect to get on the average. That applies to these degenerate conductors. And usually for a transistor in the on state, it would be somewhat close to this. Not quite. As I said, metal is where it's really very close to this picture. But transistor in its on state, when it's conducting well, would come close. Now there's another interesting wrinkle to this, and that is there are all these p-type conductors which have their conduction at energies much below mu 0. They are down here. So in that case, the conductance again, of course, is because of the tail out here. That's what gives it all the conduction, you see. Now, can you use the Boltzmann approximation for that? Well, not really, because you'll say, well, I'm using very low energies, and at very low energies, that's exponential a negative number, which is 0. So you cannot say, I'll drop the 1. I mean, if anything, you could drop that, but then you just get 1. So in conductors like this, which are called p-type conductors, what is the approximation that is used is, instead of looking at F0, you look at 1 minus F0. And what you can show is, when you look at 1 minus F0 with a little algebra, you'll get, I guess I could write this. In fact, let me just go through the algebra. You get 1 minus 1 divided by e to the power x plus 1. If I call this x like I did before, which comes to e to the power x divided by e to the power x plus 1, which is equal to 1 divided by 1 plus e to the power minus x. So in other words, the Fermi function is 1 divided by 1 plus e to the power x. But if I look at 1 minus F0, which means F0 tells you what fraction of the states are filled. 1 minus F0 tells you what fraction are empty. So if you look at what fraction is empty, that is given by 1 plus e to the power minus x. And now you see, in this energy range, where x is a large negative number, what I can do is, I can ignore the 1. And then use the Boltzmann approximation in that sense. So when doing p-type conductors, often people use the Boltzmann approximation, but the understanding is, in that case, you are counting holes. That is, how many empty states there are, rather than how many electrons there are. But all of this, of course, the point I want to make is, there is no particular need to distinguish between electrons and holes and make these approximations. One might just as well work with the exact expression that we obtained, which says that the conductance is obtained by taking the conductance of each energy channel and then weighting it according to the derivative of the Fermi function. And so the derivative of the Fermi function looks something like this. And so whatever your conductance as a function of energy, multiplied by that and integrate over energy. That's the exact procedure. Everything else is a matter of trying to understand it and gain a physical picture that allows you to think more effectively.